So there are three very exciting talks in this session. So the first speaker is Dr. Christina Giarmatzi. Dr. Christina is a Chancellor Research Fellow at University of Technology, Sydney. She did her PhD from University of Queensland and received the Springer Thesis Award. And after her PhD, she was a postdoctoral fellow at University of Queensland for a couple of years. After that, she moved to Sydney. And she has been working on quantum causality, non-Markovian processes, machine learning, and other related topics. So today she will talk about characterization of non-Markovian processes from tomography to noise detection. So let me hand over the floor to Dr. Christina. Yeah, thank you. And the participant can write the questions, queries in the chat box, or ask the questions towards the end of the talk. So yeah, so Dr. Christina, it's over to you. Thank you.
Thank you very much. Is everything okay? You can hear me properly?
Yes, you are perfectly audible.
Okay. Thank you very much. Thank you for the kind introduction, and thank you for inviting me to talk here. So let's see how this is going to go. Share. Are you seeing something normal?
Yes,
now I guess
it's, yeah. It's fine.
All right. All right, cool. So as you said, I'm going to talk about non-Markovian processes, in particular, just the full characterization of these, and a little bit of other things along the way. So this is the main paper that I'll talk about. This is with Fabio Costa, and I will talk a little bit about some other paper and some upcoming paper as well. So the motivation to do all that is to study non-Markovian noise is, of course, noise. So noise is not a good thing. I was taken when I was doing my PhD at the UQ, and this is Anders' lab, quantum optics group, quantum optics lab, and there were possums there, so they produced noise. And another thing is that quantum noise, so noise in quantum systems can be of quantum nature, which means that when we have in a superconducting chip, for example, when you have superconducting qubits, there is several qubits on the chip. And if you use only 1 or 2 qubits, the other ones can act as an environment for the system. So the noise that you have in a quantum device can be of quantum nature in the sense that other quantum systems can be your environment. So in this case, in the first case, it was the possum was the environment, and in the other case, the other quantum systems is the environment. And this is the chip from the Sycamore from Google, and these crosses over there, one color is the qubits and one color is the connections. So you have a lot of qubits, a lot of connections, and when you're using some of them, everything else can be your environment. So this is the outline of the talk. I will talk about open quantum systems and how we describe them with process matrices, and then a way to witness quantum memory in the experiment. And then that's just the theory section, and then I'll talk about some applications. So first, a theory result, a theoretical, let's say, application of the work, and 2 experiments, one finished and one ongoing. Feel free to interrupt me anytime. I don't think this talk is going to be a long talk, so there's certainly time in between for interruptions. All right, so open quantum systems. Typically, we consider a system. So here, so where's my cursor? Okay, so I can't really point. Okay, so we have a system here. We prepared it at a state row, and it evolves in time. You can see the time axis, and then you have that you can apply different operations on it. So it can be seen as different channels, T1, T2, T3. And then you have the environment. So the environment can affect all of these things that you do, the preparation of the state and the application of a gate or some general map, T1, T2, T3. And the most general thing is that the environment will affect these, but every time it affects something at a time step, so let's say T1, this can depend, this interaction of the environment and the system at T1, I mean at the operation T1, can depend on something that happened in the past. So here at the state, and so on. So the operation at T2 can depend on the state, and at T1, the operation at T3 can depend through the environment on the operation of row of T1 and T2. So this produces different kinds of noise, and we're going to talk about that. So this is the general idea of open quantum systems. The environment is everywhere, and the interactions can depend on past events, on past interactions. So then we categorize the kind of processes that produce this noise, the system-environment interaction, whether the dependence exists or not. So if there is no dependence, no time dependence of the system-environment interaction, then we say that the process is Markovian. So we use the definition of Markovianity that Lindblad and Accardi developed, and later was adopted by Pollock and by Masap and Fabio. So when you have a Markovian process, two things can happen. You either have no noise at all, so that's pretty simple. You either have Markovian noise, so you have noise, but that noise is located time-wise in the operations that you put. So in this case, that little thing on top of each T1, T2, T3 is the environment, and it can interact with the system during the operation of T1, T2, T3, but it stays there. There's no information traveling from one time step to another. So then you have the non-Markovian process. So the before, that's Markovian processes, no noise or localized noise. And then you have a non-Markovian process, which can be anything else, so anything that is not that. So this means that in the most general case, you have, so the below line is the system and the above is the environment. And you can have that the initial preparation of your system was correlated with the preparation of the environment or with the environment. So you have that joint preparation. And then the environment goes forward and it can interact with the system at the operation T1 and again at T2, and the information travels through the environment. This is some kind of pictorial representation of the information flow that can go from the system to forwards in time to the system, back to the system through the environment. So this is what happens when you have a non-Markovian process, and the noise that occurs in the system, it's called non-Markovian noise. So how do we describe these things? So as you know, open quantum systems is a really massive field, and there's a lot being done to characterize these kind of processes. And here I will show you a new approach, relatively new approach that was developed. So a lot has been done about the classical description. So let's take it time-wise in terms of time steps, what happens. So if you want to describe what happens at a single time, T1, T2, T3, or T0, then your description is a quantum state. And at the classical limit, that's just the probability distribution of some variable x at all the different times. If you want to talk about two times, how these two times are related to each other, so how the state evolves from the one time to the other, then you have dynamical maps. So that's a quantum description. And in the classical limit, this means that the probability of, it's a probability distribution conditional on the probability that was at the time before the past time. So what happens when you want to describe the full stochastic process? You want to have a joint probability distribution of all the times of all the things that happened in all the different time steps. So in the quantum case, it wasn't clear how to do that. And the answer that I will give you here is that you do it with process matrices. And here we go now to the next section, how to describe these open quantum systems, these quantum processes in time with process matrices. So what is a process matrix? So here it's a simple process. You have the preparation of the state, you apply something, some operation, and then you measure the state. So I put that thing that looks like a comb. This is the process. This is what happens. So in order to probe this process, you inject measurement stations. So at point A and at point B. So AI is the input of A and the output. AO is the output of A, BI input, BO output. So the whole process matrix formalism was developed by Oreshkov and Costa and Bruckner, and we later developed it into more parties. And the result was the following. The joint probability of the local outcomes at A and B, that's OA and OB, so local outcomes at A and B, is a linear function of, so probabilities, of the operations. So these operations M, AI, AO, BO, M, BI, BO is what happens at A and B. So it's a function, so the probability is a function of the operations and of the process. And that process can include the environment as well. So it's not really the environment, but the effects on of the environment. So essentially, you can probe what the process is by injecting these measurement stations. You take data, and with some sort of linear inversion, you obtain this process matrix, which has all the information you want, including any information on noise. This is because what A and B see is everything around them. So noise and the process, they see everything. So the data will include information about everything. So we have now a description of a general process. And now let's see, so this is through the process matrix. And now let's see how this process matrix looks in the different types of processes that I said, so Markovian or non-Markovian. So you have this Markovian process. The general one is with some type of noise that is localized. And then you inject the measurement stations, A, B, and C here. And then you can obtain data, and then you obtain the process matrix. So a process matrix that has Markovian noise will look like this. It will be composed by the components, only by the components of the process. So the state, the channel, and then identity on the output of CI. I know I haven't really defined AO, so all of these are Hilbert spaces, essentially AIO, BIBO, CICO. But yeah, if you have more questions about glossing over a few things, please let me know. And this is just a reminder at the bottom. It's really annoying, I can't use the cursor. How these are connected to the data. So probabilities, the environment, and the operations. And the environment is the process matrix here. All right, so a process matrix of the non-Markovian process. So remember the non-Markovian process, where when the system and the environment are like this, and the information carries from one step to the other. It's just not this. It's just a process matrix that cannot be written in this form. So that's all we can say at the moment. Process matrix that cannot be written on this form. Right. So I said earlier, so a non-Markovian process is one that has a memory that carries the correlations. And I'll show you this memory goes, so like a flow of information goes from raw to T1, T2 through the environment. And here I just go a little bit deeper and I will classify this memory, so the non-Markovian processes, into two types of memory, classical memory and quantum memory. So classical memory, it means that it needs a classical channel to travel from one place to the next. So this is a classical information with a double line, So you have some classical correlations on the initial state of the system and the environment. And then the first step happens, T1, and then you have some classical information traveling from one to the other, and then again. So you still have the travel of information from its time steps, but now it's restricted to be a classical information. And I put the boson here because it's a sort of noise that would be classical noise. Right, so this is how you depict it. And in terms of a process matrix, this is so the environment obtains classical information and can affect future interactions. And we proved that it can be written like this. So it's essentially, it looks like a sum of Markovian processes, a sum of process matrices that they look like, it's like the Markovian. So now we have a form of what it means, a form of the process matrix on what it means to have classical memory. And then how do you write a process matrix that has quantum memory? That would be anything else, everything that cannot be written in the Markovian form and cannot be written with a classical memory. All right, so I talked about open quantum systems. How do you describe them with process matrices, and how these process matrices look if the process is Markovian, if it has classical memory, and the quantum memory is anything that is not of these forms. So, and you'll see now the reason why I distinguished between classical and quantum. It's because there is a way to witness that in the lab you have quantum memory, that in the lab you have non-Markovian noise that is of quantum nature. So I'll show you this way of doing that, and then also applications of this. So remember, if a process matrix is non-Markovian and it has classical memory, it can be written like this. Now, we observed that this is the same set as the set of separable states. So it's exactly the same, but it's a little bit smaller, but we can assume just now that it's the same. And with this observation, we can also say that every process matrix can be seen as a state. Doesn't matter what the state represents and what is the partition, like it's a multipartite state. But at the moment, all we care about is that every process matrix can be seen as a state. It's not the opposite, it's not true, because the state of process matrix is a bit smaller than the state, the set of states. So essentially this set is a bit smaller than the set of separable states. That's okay. So this means that an entangled state that is outside of this set will also be a process matrix that has quantum memory. Because as I said, every, well, actually it's the opposite. So it's kind of the reverse. Every process matrix with quantum memory can be seen as a state, as an entangled state, and it will be outside of this set. And this is our main result, the fact that we have mapped the problem of detecting quantum memory to the problem of detecting entanglement. And we all know that the problem of detecting entanglement is very well studied. There's lots of different methods to do it. So that's why it's so nice, because we can take everything that exists for detecting entanglement and throw it to detecting process with quantum memory. And detecting entanglement is very nice because we can do it in the lab, in particular witnessing entanglement. So you can do certain operations in the lab that proves that the state is entangled. Similarly, we can do certain operations in the lab that proves that the quantum process has quantum memory. So this is very nice. Right, so I'll just show you a little bit. So one way of detecting entanglement, a little bit just in practice, how you do it. Remember the set, this is a set of separable states. An entangled state is outside of that. And by the hyperplane separation theorem, there exists a witness which is a hyperplane that separates the state from the set. We need to characterize the set through separability criteria. That is well known. There's lots of different separability criteria. And once you do that, there's some mathematical methods to do that. And once you do that, you obtain a witness. So a witness is an operator that when you apply to the state, to your state in the lab, the entangled state, it gives you a negative result. So the expectation value of that operator is negative, and it's positive for every other state, every separate state. So in the lab, what happens is that you measure an operator, and if you get a negative result, a negative expectation value, then you have proved that your state is entangled. So now let's go to the side, to the perspective of process matrices. So a process matrix that is of quantum non-Markovian noise, so it has a quantum memory, it will be outside of this set. And we can find a witness for it. So it's an operator that you applied and you get something negative. And that would mean that this conv thing, that's the process, and remember there's little boxes that the measurement stations. So the operator corresponds to operations that you can do in these measurement stations. So you go in the lab, you inject the measurement stations, you take the data that is required to measure this operator, you get a negative result, you have proved that you have quantum memory. A little bit more in detail on how it works. The same with detecting entanglement is you guess, because you don't know the state. That's the point. If you knew the state, you would know if it was entangled. If you knew the process matrix, you would have known if it has quantum memory. So you don't want to do that. You don't want to do tomography. So what you do is you guess more or less where the state is, and you obtain a witness for that state, for the guess. And you hope that this witness also works for the states, for the real state. But it's not always the case. It could be that your guess is away from the actual entanglement in such a way that the witness doesn't work anymore. It's not on the other side of the witness. All right, and I'll show you how we applied this to witness a quantum memory in some kind of a toy model of a process and into experiments. Okay, so what do you do when you have a process that you have non-Markovian noise in the lab? You suspect it has non-Markovian noise. So this non-Markovian noise, it could be classical. So the reason, not only the reason, but the correlations that are between the different time steps could be classical correlations, or it could be quantum. So it could be that not only the environment is on quantum nature, so not only the environment is different, other different qubits, but it also produces quantum correlations among the different time steps, which means that there's some sort of entanglement in time between the different components of your device. What can we do? So the great thing, the perfect thing to do would be tomography, which means you inject these measurement stations, A, B, C, and you take data. You take, in particular, you take informationally complete data. And if you want more details, what happens at A, for example, A should measure informationally complete measurements, should measure the state and should prepare every state on a basis. So informationally complete preparations. So measures the state, prepares, measures, prepares. That happens for many rounds of the experiment. And the same thing, this is what B and C do as well. So you take data from that and you calculate the process matrix in a procedure similar to how you calculate a state from measurement data. You do some kind of a linear inversion. Right, so, and then once you have the process matrix, that's the full description of your process. And any kind of noise that you have in the process, it will be seen in the process matrix. In some hidden way, of course, you have to find good ways to investigate it. And I can talk more about it a bit later if there's questions. But the ideal thing to do when you have quantum, when you have non-Markovian noise in the lab, you do that. You inject measurement stations, you obtain the process matrix, and then you have the full information. And then you can find different measures of non-Markovian noise and different types of non-Markovian noise through the process matrix. But once you have that, you're done. You have all the information that there is to have. It's not so great, of course. There's a small caveat. It's just that it's difficult to obtain this process matrix because it's difficult to inject measurement stations, and it's also difficult to do tomographic operations at A and B, C. These informationally complete things, I said. But we'll talk about that a bit later. Another thing you can do is you can witness quantum memory. As I explained earlier, it requires less data. So you still have to inject measurement stations. You take a bit less. No, I don't really know if it's a bit or a lot, but you take less data. And from that, you can have a guarantee that you have detected quantum memory in the lab. So with everything that I've presented so far, this is the usefulness. This is what you can do. And I just wanted to specify that this is a really big deal for experiments. This is the first time that they can, if they can obtain the process matrix, it's the first time that they can really fully characterize a multi-time process that has quantum memory. All right, so now these three examples that I promised you. One is theory and two is experiments. So this is the theory one. We constructed a process that we wanted it to be Markovian. And we wanted to have some parameters as well to change the kind of Markovianity. So here, the bottom line is the system, the top is the environment. System and environment are fully correlated, maximally entangled, 5+ state. And then you have a unitary evolution at that U over there. So EIO, E is the environment, and A and B are the measurement stations that you inject there to probe the process to obtain the process matrix. So this is the 5+, this is the unitary, it's an evolution according to a Hamiltonian, and this is called, I forgot, the inverse Ising model, I think, not sure. This XX, it means it's a dipole-dipole interaction, and the XX, it means that the two dipoles want to align together in the X direction, and the J is the strength of this correlation between them, and H is the strength of a magnetic field, so it's an external magnetic field that it wants to align the dipoles separately in the Z direction. So Z identity, identity Z. Through some way, we obtain the process matrix. So we just see the circuit, you write down a couple of things, it's written in the paper, and we obtain the process matrix of this. And the process matrix, of course, it depends on three variables. One is J, the variable of the Hamiltonian, H as well, the strength of the magnetic field, and T is the time that U is applied, time of the unitary. So these are the results. Here we plotted for different H, not plot, but it's more like a heat map. So for each H and J, the two axes, there is one process matrix. We fixed T equal 1. So each pixel of this picture is a process matrix for a particular J and H. And then we applied the PPT criterion, which I didn't explain, I think, positive Parsons transpose. It's a way to detect entanglement. I won't explain it, maybe if there's a question. So it's a way to detect entanglement. And this, the color of each pixel, so it's a process matrix, the color is this trace that I showed you earlier, trace of the witness with W. So if it's negative, so anything that is not yellow, it means that we detected quantum non-Markovian noise on this process matrix. So again, every pixel is a process matrix for a particular J and H, and the color of it, if it's not yellow, we have detected quantum memory. I really don't know why the structure is like this. I guess it has to do with the Hamiltonian and how when you change H and J, the different stages are decorrelated. Sorry. These are the different stages. So phi plus and u, these two are correlated. There's the environment that carries the correlations. And when you have non-Markovian noise, it means these two are correlated. And I guess for different values of u, for different values of j and h, you have correlation and decorrelation. Like they get not correlated. Another thing, so one thing that was the witnessing quantum non-Markovian noise, but I told you that you can do two things. One was the witnessing and the other was the tomography. So here we didn't need to do tomography because we already had the process matrix. So from the process matrix, you can estimate a general non-Markovianity, a general non-Markovian noise. So not quantum, not classical, just a general. And there's many ways to do it. We chose the relative entropy. That's the relative entropy. It's not very nicely written there. It's relative entropy of the W of the process matrix with respect to its closest Markovian. So when you say relative entropy, you need to say two things. So it's the process matrix with respect to its closest Markovian. So obviously, when the relative entropy is zero, you have that the process is the same as the Markovian, so it's Markovian. So every time it's yellow, it's Markovian. And again, everything that is not yellow, it has some general non-Markovian noise. And this is a paper where we published that. And I just wanted to, I think it's like this. Yeah. This is how you see the two things. So every pixel is the same process matrix. And here is general non-Markovian, everything that is not yellow, and general quantum non-Markovian, again, everything that is not yellow. Any questions so far before I go to the experiments? Oh,
so excuse me, I have a question.
Yeah.
So like, while writing this process matrix, like you also need to specify the basis for the system and environment, right?
Yeah.
In the similar fashion. So how would like you showed us like for for Markovian process, what the process matrix will be, and if there is a classical memory, what the process matrix will be, that big summation over all the separable kind of.
Right.
So for what, how different this process matrix for non-Markovian will be? Like, is it too complicated to show? Like,
it's just it's like an entangled state. It's not written in that form.
okay, you can't
It's,
write in that like matrix test, like outer product of the matrices.
Sorry?
So we can't write that in terms of outer product of the matrices, like the way we wrote earlier.
Yeah.
Okay.
Yeah.
Okay.
And in case, like, as I said, every process matrix can be seen as a state. And a process matrix that has quantum non-Markovian noise will be an entangled state for a particular partition. And I can show you the kind of partition. Here, so down you have W, AI, AO, BI. So this lives on the Hilbert spaces AI, in the picture AI, AO, BI.
Mm-hmm.
And the partition would be, oh my God, I don't think I can remember. I think it's AI and AOBI. So this process matrix is exactly like, if you see it as a state, it would be a row that is a bipartite state. The first part will be AI, second part will be AOBI, and across that partition, this state will be entangled.
Okay. Mm-hmm. Okay. So this witness you are saying that uses like whether the state is entangled or not, right?
Yeah.
We can say.
Yeah. So basically, the witness for quantum memory is exactly, you see the process matrix as a state, and you try to find a witness for the state that I told you, for the state, for that partition, for that big partition of the state.
Okay. So
And once you have that, this state is entangled, then it's exactly this. You're saying that this process matrix has quantum memory.
Okay. So if we calculate this witness using this process matrix, we can be sure that there is a quantum memory in this system.
Yeah.
Okay, thanks.
No worries. Anyone else? All right, cool. So there's only 2 more experiments and we're done. So it's quite early. Detecting classical memory with AI. So that was the first experiment. So after we had that method and the paper, we thought, okay, let's go and do something with experiments. At the time we were at QIQT, so me and Fabio both at QIQT, and we have the excellent lab of Andrew White and nice photonics lab, and also the lab of Jackie Romero. And so what we did, so they had again, they have the resources of having a photonics lab. So we thought, well, we can make a process matrix with photonics. So you have photons and you have various degrees of freedom. I think we used polarization, and we can make a process. So you have a preparation of a state, and then we can apply different things and then measure. However, if you do that, so with photonics, usually you won't have a quantum memory. You might have, but I think it was a bit complicated to make it, to manufacture it. But naturally, you wouldn't have. Maybe you would have some classical memory and maybe some quantum memory because of other photons flying and interact with each other. But it was really tricky. So we thought, well, we'll just simulate it, just to see if our methods can be applied in the lab, because in the lab there's all sorts of things happening. There's also sort of noise. So we wanted to see if it's going to work. So what we did is we made this process. So this is the only slide I'm going to have on this experiment. So all the information is here. So we created this process. We prepare a state that's in polarization, and that's a photon going. And then we apply the unitary U1 and then a unitary U2. Ignore the UP and M. So that's the process, rho, U1, U2. And we wanted this to have memory, to be non-Markovian. And it was a bit hard to put it, to entangle them, to make them quantum memory. So we thought to do classical memory. So this is why I say detecting classical memory. So in order to put classical memory, essentially, you correlate all these 3. So there are correlations in these 3 components, rho, U1, U2. And practically the way we did it, all this was automated functions. So U1, U2 was wave plates, but they were motorized. The state preparation, of course, you can automate it as well. I guess, I don't remember, but it was maybe a stable state, and then we put motorized things in front of it to alter the preparation. So then you can do that. That's great. And you can prepare many different things, and you can have different types of correlations. We discussed this in the paper. Now, how do you probe this? Then we put this UP and M. So UP is a unitary. I know it's not the informationally complete thing I said earlier, but we wanted to do it with less information. So we just put a unitary there. It's a probe thing. You put a unitary, and then we had a measurement in the end. And so far, I didn't tell you how you can detect classical memory, because you can't. The only way with witnesses and with witness stuff, with a guarantee, is entanglement. You cannot guarantee, even with separable states, you cannot guarantee that you have separable states. You can guarantee if a state is entangled. That's all you can do. So since we had here classical memory and we don't have a way to detect that, then we thought we use AI, which means you take the correlations there, you have the process matrix, you know what correlations it has, so you know the classical memory, the amount of classical memory if you want, and then you have the data. So you put the data into an AI machine and you train it, you tell it, this is the data, this is the process matrix, it has this amount of non-Markovianity. And again, as I said, this was motorized, so we could have thousands and thousands of data, and we put in this AI, and then eventually the AI learned, and just seeing the data, it could tell us what's the amount of correlations that existed in the process, just by seeing the data. So this was published there, and now I'm going to go to experiment number 2, and that's the full process tomography. And that's what I meant in the title, full process characterization. This is what I meant. We do full process tomography, and we did it with superconducting qubits. So this is a collaboration. The QIQT was again, Arkady and Tyler are the experimentalists, and in the theory part is me, Fabio, and Alexei. So what we did in the lab, or the experimentalists did in the lab, we have the system. So they have superconducting qubits, which means they have a chip, and that particular chip had 5 qubits there. We used 1 qubit as the system, and T1 and T2, this is the process. This is what was happening. And the purple things there are the measurement stations. And the measurement stations, we prepare a state, then we measure a state, prepare again, then measure. That's the data we have. And the process going on in the background is first, the process is the system that undergoes through T1 and T2. And in our models, we had that the environment is just 1 more qubit. And it's a nearby qubit, nearby in the chip. And T1 and T2 is free evolution. We didn't want to do anything too fancy. That was the first effort that we wanted to do to apply this method in the lab. And in this situation, there's no simulation. We didn't artificially put any non-Markovianity. We wanted to genuinely see if there's non-Markovian noise, and if there's of quantum nature as well, non-Markovian noise in the chip, just because of the other qubit or of the other qubits. But in the model, we only had 1 qubit. So this is the result. So by taking this measure and prepare data, we obtained informationally complete. So we obtained all the information we needed for tomography. So we did tomography, which means we obtained the process matrix. And then from the process matrix, we had everything we wanted. And from that, through some measure, like it's not complicated, it's very easy, we estimated the amount of general non-Markovian noise. So if it was 0, it means it was Markovian, but as you can see, it's far from 0, so it was non-Markovian. So we did this for 2 things, 2 systems, 2 devices. One is the 5-qubit chip at QIQT, the University of Queensland, and the other one was at IBM. The device was IBM Perth, so it was in Australia, and it's a 7-qubit chip, and it had much less non-Markovian noise. So as I said earlier, you can do 2 things. You can do tomography, or you can do witnesses. If you have all the data, you do tomography. You don't need a witness to witness quantum memory, but we as well tried as well the witness, but it didn't work just from not knowing the data. After you know the data, you can see that it has quantum non-Markovian noise, because once we had the data, we had the process matrix, and from the process matrix you see that the state, and you see if the state is entangled, and indeed the state was entangled. So from doing tomography, we had information about the general non-Markovian noise. We see that it was there, and we also saw that the state was entangled. So it did have also quantum non-Markovian noise. And I think that's it. Yeah, so I told you a general description of what happens when you have an open quantum system and how we describe it with process matrices. We put these measurement stations, we probe the process, and we gain all the information that is there about the process and its noise. Then I distinguished this non-Markovianity in terms of classical and quantum memory, and I showed you a way of how to witness quantum memory. Then I showed you how you apply this in a toy model, in some theory example of a quantum process that has memory. Then I showed you that with AI, we could estimate the amount of correlations, classical correlations, that we injected in the photonics experiment. So basically classical memory or classical non-Markovian noise. And then we made an experiment with superconducting qubits at UQ and at IBM. That is an old picture. And we basically got information of the non-Markovian noise and of the quantum non-Markovian noise because the state wasn't known. Yeah, that's it. Thank you.
Yeah, thank you so much for this nice talk. It was a very well organized talk. Yeah,
Thanks.
so we have time for questions. Yeah. Okay, so I have a couple of short questions. So when you introduce the measurement stations in between the interaction, like time evolutions, so those measurements can be in general POVM, right?
Yeah.
So and do you assume that? Yeah.
They should be. They should give you full information.
Yeah. So do you assume that measurement can affect the environment or that?
Yeah, that's a really good question. Of course it can. Of course it can. But in this picture, like for this to work, you don't want to, because then there's other complications. So in this picture, as you can see, these are isolated just on the system. But yeah, you're right.
Okay. Yeah.
So in the lab, of course, you say to them, try to not disturb the other systems.
Yeah. Okay.
And this is what happens in general as well. So even if we don't tell them, if they have a system and they want to only probe that, they will try to not disturb the other qubits because of these kind of things, because then the correlations will carry, they will create entanglement in time. So the way that they do this in superconducting qubits is they have every qubit has a resonance frequency, which means that the microwave pulse that you apply to that qubit to interact with it has to be of different frequencies. So you apply different frequencies for each qubit, and these frequencies have to be a little bit apart so that every time you probe a qubit, you don't probe the environment. So in the experiment and in every normal experiment in superconducting qubits, they will do that. They can tune the qubits. So they will tune the qubits to be far away from each other in terms of their frequency. And in this example, where we had T1, T2 was just free evolution. So we didn't do anything. It wasn't like a forced thing to do but I guess someone will need an algorithm that needs 2 qubit gates. So then they will have to have them close together to apply 2 qubit gates. But when they apply measure and prepare, we will have to tell them, I don't know how it will be possible, but we will have to tell them, you have to not disturb the other qubit.
And the other question was like a very basic question. So like, is there any mathematical characterization of process matrices? Like is there any like set of mathematical properties that define a process matrix?
Yeah.
In general.
Yeah. Positive matrix, and there is an operator that you can apply to it, and it puts you to the space of valid process matrices. So it's the same as the states with extra conditions, because when you talk about the process, you need to obey causality. You need to obey that this system happened first and the next time step happened second and third. So there are some correlations between A and B and C that are not allowed because it would assume that it would imply that B affects C, but also C affects B in some sort of causal loop way. So it just, yeah, it's well known. It's not difficult to obtain them, and you just write them down.
Okay. So yeah, Ranjit Singh has a question. So
yeah, thank you for your talk. I have few questions. So the first one is, when the system is not opened or conserved, one can check the output results by, or intermediate results by checking energy conservation or commutation relations. But in case of open system, how do you verify output results?
How do you verify the output results?
Yes.
What do you mean verify? Verify what?
For example, energy conservation in conserved systems. Because when the system is open, then the energy is not conserved. So in this case, how do you verify?
So how do I verify that the system is open?
The results are correct or according to your expectations.
Right. How do I verify? So the results at A and B and C, they're going to
Yes.
be probability. They're going to be probability distributions of what happens at A and B and C.
Yes.
I don't know. It's just measurements. We just
Okay.
measure and prepare, measure and prepare, and we take the measurements. Then on every experiment is different. You have all these counts, but you just calculate probabilities from the counts.
Okay.
So I don't
Thank you.
think we go through another verification step.
Okay. So second question is, in optics, noise sources may be from optical devices, that is thermal, vacuum noise. So my question is, what type of noise mechanisms you consider in your calculations and photonic experiments?
What type of noise you mean? Just to estimate the sigmas of whatever you have, or the noise that I want to find, the noise of like the non.
Yes.
The second. Yeah, in the second. So as I said, it's a bit complicated to have this kind of noise in photonics. It is possible, but the mechanism is a bit complicated. And so in order to not investigate that, we just simulate it. This is why we simulated the correlations between the rho and Y1, Y2, not simulated, but we just injected it by force. So we put artificially correlations between rho and U1 and U2. And we did that by actually correlating them. So every time we would make U1 a little bit like this, so this is like a wave plate that changes the state. So every time that this would go a little bit here, this would go a little bit here. So we put noise and we correlated the noise. We put correlated noise between U1, U2, and as well as rho.
Thank you. So the last question, could you please name the software packages you used for AI or detecting classical memory with AI?
It wasn't really anything fancy. I can't remember. Just maybe neural networks, I think. But we also, I don't know eventually what we reported, but I'm sure we reported everything. But I remember that the first thing I tried was linear regression and then polynomial regression. And already with polynomial regression, there was really good results. The probability of success was around 82% already with polynomial regression. So apparently a polynomial function was connecting the amount of non-Markovianity and the data that we were getting. And then we did something a bit more fancy, but we didn't get much better. I think with neural networks, we went to 87%, something like that.
Thank you.
No worries.
Yeah, so any other question from the audience? Yeah. So if not, we thank Dr. Christina again, and yeah, and maybe we'll move to the next talk. Yeah.
My pleasure.
Thank you. Yeah.
Bye.
So we take a break for a few minutes, 2-3 minutes, and then we will start again.